Okay, so yeah, let's take some inventory of stuff. So your final project has been released, as you guys hopefully at this point all know. It's due June 1st. That's going to be a Tuesday. Homework 3 was just released yesterday, and that's going to be due that Thursday, June 3rd. And then of course the only exam for the course is going to be week 9, which is going to be Thursday, May 27th. So a lot of deadlines coming up. You still got some time, but I know you'll have the tendency to look and you'll see June and you'll just be like, I'll worry about that later. But please don't do that. Cannot emphasize enough. So yeah, I guess any questions in terms of like logistics for the course? Make sure I'm looking at the chat here. Okay. No, everybody's good. Cool. All right. So, okay. So firstly, I just wanted to kind of just do a quick recap. Tammy, I don't know if Tammy's even on the chat here, but I need to acknowledge the fact that she literally manifested an in-person graduation. And then like literally an hour later, you say, I was like, yeah, we'll do that. You can invite 2 people. So Tammy, I don't know if you're taking any requests, but like if you want to like manifest no exam for the course or something else, start charging.
I have to manifest with Isabel. That's the only way it works.
I see.
Not me alone.
Yep. It's like what was it? Captain Planet. Yeah, your powers got to combine.
Lionel, you should be the one manifesting no exam.
I don't think I got the power. If anything, it might like be the reverse. I'll try to manifest it, and then it'll be like, actually, we'll do a final exam too. You don't want to mess with this. It could backfire. I feel like we've got a good thing going with Tammy. I think we just kind of default to her, But yeah, so I did have to acknowledge that because like literally she was like, we'll do an in-person graduation. And then an hour or 2 later, I was like, okay, sounds like a good plan. So I did also want to talk about, I did want to confirm our week 10 logistics. Oh yeah, Tammy, it's got to be in Dogecoin for sure. Like no question. Can't be accepting any other cryptos. Let's see. Okay, yeah. So I also want to talk to you guys week 10. I know I kind of teased this, but again, week 9 is our exam. Week 10 is when everything comes due. And so then there's this whole like, theoretically we have discussion, but maybe we don't. So it's really up to you guys. So I put together a poll so we can decide what we're doing. Okay, so this is going to be week 10 options. So I will let the collective council of elders decide. You have 4 options to choose from. First option, you can just cancel it outright. Second option, we can do a topic specific to data science. Third option, I'm not gonna lie, I was pretty proud about this. Just let me alliterate for 2 hours. And then fourth option, we can just hop on the Zoom and chat. So I will let the fates decide this one.
For the third option, could we learn like about what you do?
We can talk about whatever. I mean, the idea would be, I guess that would be sort of an open subject. So when you say learn about what I do you mean like my kind of research or?
Yeah, don't like grad students love talking about their research? You haven't really talked about yours.
Not this grad student, but yeah, so I could totally do that. But all right, to make it easier, I would say let's put that under topic 2, because I could totally like walk through some of my research in the context of data science. So that would be option number 2. I think option 3 is just non-data sciencey related conversations. So you're able to change your votes, right? You're not locked in once you vote.
No idea.
Okay, so option number one, cancel. So not seeing a lot of love for canceling it or an unstructured thing. Not seeing a lot of love for data science. Clearly we have failed you all because you have no love for the data science, for the science of the data. More love for yeah, I'm not even gonna tell you how much time I spent working on that alliteration. Should have been working on my slides for today. Instead, I was doing that. Okay, we got 94% of the vote in. I think we are voting to do a random topic. Okay, then end poll. I'm gonna share results. We have a runaway winner here to let Lionel limitlessly lecture, leveraging lessons learned, living leisurely. Whew. Okay, I have a follow-up poll in the offhand chance that that was the winner. See, I came prepared with the polls. We're going from like, we're overdosing you on polls today. So if you want to talk about random non-CSE stuff, I have some options for you. So we can talk career discussion. That's something we did last quarter. I mentioned this before. As you guys know, I'm like old. I've been working for over a decade now. This is sort of back to school for me. So maybe I have kind of a little bit of insight into the whole career aspect. So we can talk about that. Yeah, I also have degrees in economics, philosophy, and all manner of healthcare related stuff. And actually my day-to-day job is on that. So we could do that. And then I also mentioned my particular passion for writing screenplays. So if you ever want to talk about the art and joy of writing a screenplay, we can do that. Okay, so I'm seeing here a little bit more mixed in the topics. We don't have a runaway winner. Actually, career discussions kind of pulling ahead a little bit. That's cool. I got some baller slides for that one. Nobody wants to talk healthcare. Nobody wants to rip about health in the US. It's a cool topic. Yeah, economics is cool. I taught a summer discovery thing here about economics. And so I did like a whole seminar on the evolution of economic thought, starting with sort of pre-Adam Smith, the Wealth of Nations, and just kind of how the discipline evolved, because the whole concept of an economy didn't really exist prior to industrialization, just kind of thinking about how that evolved. So, but okay, we're at 94%. I think that's what we had last time. Let's see here. Yeah, I know. I wanted to do one of these days, I'd love to talk screenwriting. I just feel like it's such a fun topic, but it appears our overwhelming winner was career talk. So y'all just want to make the Benjamins. Y'all just in it for the cheddar, not for the love of the game. Y'all just want to be hustling. All right. So week 10, we're going to have a career talk. So yeah, pretty evenly mixed, but it's a cool topic. Yeah, we'll talk. I try to do with that, kind of mix in a few things we don't really talk about. At least Career Center doesn't really talk about a lot, but like things like how to network effectively, because everyone tells you got to network and nobody actually tells you how to do the damn thing. And things like that. How to kind of ace your interviews, just do better with that. Different approaches you can take for that. Identifying the right type of job. That's another thing people really don't spend time doing. Everyone's like, just apply, and whoever gives you a good offer, just run with it. And people don't really actually spend a lot of time thinking about where they'd want to end up and what they'd want to be doing. And I can't tell you the amount of people like I'll talk to that a year out, like I'll be talking to them and, they've just gone through leak code and all the stress of that. And then 6 months later, I'll be checking with them and like, yeah, I'm applying for jobs again. I kind of hate where I ended up. And just like, can you imagine how miserable that is. So, just investing like a little bit of time to be like, do I really want to work for this company? Just could make a huge difference. So we'll talk about that a little bit. And by the way, because I feel like I got very lucky with my particular job, but nobody ever sat me down and talked to me about this. It just happened to be that it worked out really well for me. But someone had been like, here's really what you need to think about with a job beyond just the usual. So, all right, so that's going to be week 10. Cool. Okay, so let's see here, and then let me get y'all out of here. So today, make sure I didn't read. Okay, yeah. Oh, yeah. Sorry, Chelsea. Can I put you on blast? I don't want to call you out, but we actually talked a little bit about the networking, and you became like the grand master of networking. I'm like in awe of what you did. I don't know if you want to talk about that briefly, but.
Sure, yeah. So I talked to Lionel about career stuff in the fall because I was like panicking about like not having a future. And then eventually, through Lionel's instruction in networking, I like created a Google spreadsheet and I like latched onto a couple people and then like infiltrated. And then eventually now I have a data science internship for the summer. So success story.
Yeah, I'm not gonna lie. And by the way, if you could come week 10, because I wanna actually have you talk about your experiences, because you like went out and just like did amazing. And yeah, I was like blown away by how well you did with it. So
All credit to you, Lionel.
all right, so that's what's going down. Okay, so let's see. Yeah, so today I wanted to talk about some of the things that you're going to kind of need for project 3. Fill in some of the theoretical stuff as well as some of the kind of coding examples. Pretty much give you most of the code you're going to need for that. Then touch upon some topics that are going to be relevant both to the project, the homework, and even possibly the exam. That's my goal for this week. Next week, we're going to prepare in earnest for the exam. And then, let's see, the next week is going to be week 9. So I think we'll kind of review the exam and then talk about any kind of miscellaneous topics for projects and homeworks. So that's what I'm thinking, guys. How's that sound? All right, cool. I will take that as rousing assent. So one of the things you'll notice that like for this project, we ask you to do kind of build on some of the approaches you've done previously and sort of expound on that. And one of the things that we ask you to do here in particular is to use regression for feature selection. And I'm going to just note, by the way, that we do ask you specifically to use logistic regression, and you can do logistic regression, but sometimes that doesn't particularly work. And if that doesn't work, you can use OLS. You can use sort of a standard linear regression for this as well. There's reasons why a logistic may or may not work depending on some of the characteristics of your features. But there's a reason for kind of doing this step explicitly. There's actually 2 reasons. The first, and we're going to spend a lot of time talking about this today, is model optimization, feature trimming. And that's something that we have kind of touched on a lot in this course about, we've talked about that with like one-hot encoding and the dimensionality of your data frame and how that leads to overfitting. And we're going to spend some time talking about the mechanics of that in detail. But just to acknowledge that there are multiple approaches to dimensionality reduction. Pop quiz, does anybody here remember a approach we've already used for feature reduction? Maybe. Okay. Is there some specific thing that you can do to prevent overfitting that in the yes. Okay, Isabel, awesome. There we go. Nailed it. Oh, Daniel, you got it into, okay. That was a tie. Cool. Okay, yeah. So an L1 regularization, right? So that doing a lasso regularization, because it zeroes out the coefficients, you're effectively trimming your features. So that is an example of using, using in that case feature regularization to trim the dimensionality of your data set. So that's a great example of that. We're going to learn two methods today. The first one we're going to learn is using regression and sort of statistical analyses to kind of help decide what features to include and what not to include. There are others. Actually, this is, there are multiple kind of approaches that you can take to doing feature selection. These are just sort of a handful, but this is kind of the first reason you may want to do something like this. Another reason that I wanted to highlight is data collection. And particularly when you get into some of the more complicated models for both data engineering as well as sort of data modeling, you get increasingly into these sort of black box type approaches that kind of obscure your inputs and outputs and the relative importance of that. Neural nets, for instance, famously being these essentially black box things where you feed in a bunch of features, there are a bunch of hidden layers, back propagation, convoluted sort of feedback loops, and by the end of it, it's getting you a nice classification, but you have no idea how it's getting there or how it's getting the result it's getting. And that can be fine from a model performance perspective, but and if your goal simply is to optimize the performance of your model, then you're great, you're done, the work is done. But in a lot of cases, the data that you collect isn't static. And oftentimes part of your job in working with sort of either a company or a client is to help them understand what data is important to them for their model. So, and just to give you an example of this, you may be collecting a variety of data to try and predict something. Let's say you're trying to predict, so this is an actual project I'm working on, predicting the chance that a patient who has had surgery, who post-operatively is assigned narcotics as pain medications. What is the likelihood that they may develop a substance abuse disorder based on that usage? And so, so we're collecting a bunch of data and we're going to try to build a predictive model around that, right? So we're going to try to optimize that. But part of the work we want to do ultimately is also identify what information is most characteristic of that prediction. So, because we might say, it's important to physicians going forward to say, if you want to really accurately assess the risk of a patient, yeah, we have this model you can plug data into, but we also want you to understand that like these are the features that's most important to collect. If you have to prioritize collecting certain things, try to collect data on XYZ, because these are the features that are most important to sort of accurately classifying an individual. So thinking about kind of data science and a lot of your models as living, breathing things where there's this ongoing challenge for data collection, doing something like this can be really, really important just to kind of help you understand what data is most important to your model. And again, the idea isn't that these models are necessarily your final result, quite the opposite. Typically, using like a basic OLS or a logistic classifier won't be your final model, but precisely because it allows for this visibility, it allows for this tractability, it's usually a really good step to take just to, again, to kind of understand how the feature space is evolving. So let me kind of pause there and see if that kind of, if y'all are tracking that. Okay, cool. So I have some sample code here built on my poor little avocado model. But the thing that we're going to use is, so up till now, we pretty much relied pretty heavily on scikit-learn for much of our learning models. Another really popular library is stats models, which is a really great open source thing that focuses specifically on, not just generating sort of those basic models, but in generating the statistics that underlie it. So we have some code here. I'm going to pop over to, where's my browser that has the code? Okay, that's not it. That's not it. That's not it. Ah, there we go. Okay, so this is our poor little avocado data. So everything from here, if you pull this up, link is on the website. It's also on the slideshow. So this is everything we've done previously. Nothing really new here. Nothing new here. The cross-validation stuff you've already seen. New material, if you scroll down, new material for May 14th is right here. So I have code for two things here, the stats modeling and then dimensionality reduction. So that's code for both of those things here. So the first thing you'll see, it's really, really easy to do. You just kind of define, just like with your scikit-learn, you first import that, then you create a specific instance of the model. In this case, we're doing an OLS model because the logistic classifier didn't work with the with some of the specifics of how we'd one-hot encoded it. So it didn't quite work well. So we had to do an OLS for it. And then you just input your labels, your features, and then you run the fit thing, and then you output the results here. And then when you have those results stats, you can just output a summary for it, and it'll print this nice little table here. And if you're looking at this, we'll run through some of sort of the key highlights of this, but you see here, they have some nice overall model level statistics here. And then for each feature in your data frame, it'll give you the associated coefficients, the standard error, t-score, p-value, and I believe those are the threshold values for the 0.05 levels, I believe, or 0.025 levels. Oh yeah, because it's a 0.05, but it's a two-tailed thing. So that's why it's 0.025. It's still doing a 0.05 overall, but because it's two-tailed, you look at the values on either extreme. So that's what that's looking at. But we'll go through that. But yeah, very easy to generate that, very easy to export those models. And so, oh, that's funky. I had a transition there I didn't mean to do. So feature interpretation, I forget, honestly, if Professor covered these early on when we were doing linear regression, but if he didn't, really quickly, we can just run through some of the kind of the key highlights. So R squared here, up here at the top of your regression results table, that's a really, really useful statistical measure that kind of indicates goodness of explanation, if you will. So it looks at the variance. It compares the variance of your labels or your independent or your independent. No, the X's are the independent. The Y is your dependent. Yeah. So your labels are your dependent values. It looks at the degree to which the variance in your labels is explanatory, is captured in the variance in your features. So that's really what we're looking at here. Maybe unsurprising, given that we're running an OLS, that's not particularly good. This is judged on a 0-to-1 ratio. So we're really looking at about 50%. That's not terrible, but that really isn't great. That says that there's a lot of variance in our labels that we're really not capturing in our features. But again, this isn't our working model. We're really just using this to try and determine the importance of our features. The sort of critical values that you want to look at to get to a feature level thing are your F stats and your T stats. So an F stat is both of these look at, it's an ANOVA, which is an analysis of variance test. And it dives into, it's similar to conceptually to an R squared, but it's basically saying the degree to which variance that you see in one population, in this case, your labels, and the variance that you see in other things, the degree to which they sort of track each other. And so if R squared looks at sort of the overall goodness of fit of that variance, this really says that either F stat is looking at the overall model and T stat looks at the individual features. To what degree do those the variance kind of move in concert with one another? To what degree are these correlated, and to what degree is a shift in one predictive of a shift in the other? And so those are typically values. Those are positive values, values greater than, I think it's greater than 0 always. No, I'm looking here and there are literally negative T stats on the thing. But you look at sort of the relative magnitude of these things. There's kind of a question of what a significance threshold is here. And there's two ways to look at that. The first is you have to check the p-value first. And then related to that, you then have to look it up because it depends. The actual significance threshold depends on the size of your data frame, the number of your features, And so there's actually sort of tables that you would look up to see what the significance levels are. But then related to that is the p-value, and p-values is probably the kind of statistically, that's kind of the most famous one, but that's the whole idea of what is the probability that we are seeing these particular values given that the null hypothesis is true. And so the null hypothesis, again, is the idea that there is no intrinsic link, that these is pure chaos. There's no underlying sort of pattern to these, that your features are not predictive of your labels. It's pure chaos. Your alternative hypothesis is that actually, yes, there is a meaningful relationship between these features. And so your sort of critical threshold is saying, well, when that probability that what you're seeing is purely a chance coincidence, when it falls below a certain critical threshold, we reject that and we say at this point, we're fairly confident that there is a relationship. And yeah, so again, the important thing to say here is that it's important to say exactly what a p-value is. A p-value doesn't specifically say, doesn't say conclusively that there is a relationship. It says that you are confident enough to reject the null hypothesis. And the null hypothesis is there's no relationship. And if your probability is low enough, you say, okay, I'm fairly convinced that that null hypothesis is no longer true. And the standard thing you see here is in most scientific things is 0.05, which is essentially 1 out of 20. And again, that's just simply saying that if the chance that these particular sort of set of features occur could be the result of just a random chaotic thing that has no relationship between the features and the labels, the chance of that happening is less than 5%, then we say, okay, there's probably a relationship there. So generally speaking, what you would look at is if you're looking at the significance of your individual features, you'd want to look at your p-values. You'd want to make sure it crosses that threshold. So just eyeballing this, if we're using a threshold of 0.05, so we can see X1 and X2 clearly meet that threshold. Everything else in the data frame kind of giving us problems there. It doesn't kind of clear that probabilistic thing. It's looking a bit too chaotic. And sure enough, if you see this, the associated t-values are very high. So chances are that both of these, whatever these two features are very highly correlated with our label. The rest of it, these t-values are very marginal. Chances are they're not critical, and particularly with that. So if we decided we wanted to trim everything down here, we'd probably be okay doing so. So let me kind of pause there, see if you guys are kind of feeling that, if you're vibing that. I know I've literally, anybody here who's like a stats major or minor is probably having an aneurysm because of how badly I have butchered the explanation of basic statistical measures, but I guess good enough for government work, maybe.
I have a quick question.
Hit me.
Oh, sorry, Daniel, you can go first if you want.
No, take it. I'll go.
Okay. So could we also like just run a logistic regression and then exponentiate the coefficients that the model like gives to see what the feature importance is?
Yeah, okay, so that's a really good point. So the coefficient is also, I didn't kind of highlight the coefficient. The coefficient is also a really important part of this because obviously coefficient speaks to the magnitude of the shift associated with it, right? But and so, you know, obviously you could say a higher coefficient, clearly the more impactful that feature is. The one caveat with that though, is that, and this comes back to sort of scaling your features versus non-scaling your features. A lot of models like logistic regression are scale invariant, which means that they will try and correct for differences in scale. So you may have a feature with a very low coefficient that actually is very important. But the reason the coefficient is so small is because maybe the magnitude of your X variable is high. And so overall, the shift is important, but the coefficient may not necessarily represent that. And so now you might say, well, if I just scale all my data between plugging in my model, would that then correct for that? And it probably would, but I want to caution just looking at coefficients because, sometimes there are very sort of critical, nuanced shifts in your model where a feature may have a very small coefficient, but may be critical to achieving certain accuracies and certain decision thresholds.
Yeah, I was just wondering, like, because if we pipeline the data and scale everything and then run it through logistic regression, when you take those coefficients and then like exponentiate them, so like e to whatever the coefficients are, that would indicate like the change in the odds by like a factor, right? So wouldn't it like tell you how important it is because it tells you like how much the odds change for each of those different features?
It would, yes. And so, and so you wouldn't be wrong by looking at analysis, particularly again, if you've scaled all of your features. The one thing, so there's two things I'll caution with that. The second one we'll touch with in a minute when we get to principal components and that thing. But the other thing is just thinking about it on the margin where, particularly if you have a very sensitive decision threshold, marginal change in a value may be critical to a certain classification. And if you have a feature that maybe has a very small sort of magnitude, but is very closely kind of correlated, like you look at their P and T values and you see like there's a very strong association of the variance, it might be like that's the feature that kind of kicks it above a decision threshold. And by eliminating that, you actually, even though it doesn't seem to be significant, it could actually dramatically impact performance.
All right. So do you recommend that we do both logistic and the linear regression when we're looking for feature importance?
I would. So I would say if you can run a logistic, do that over an OLS, because remember OLS. So the whole reason we got away from linear regression in the first place was that it was kind of a poor fit for classification. The reason I'm running an OLS here is when so one of the characteristics of this particular data set, when I one hot encoded my thing, I got for region, I got a bunch of sort of essentially zeroed out features, and basically a logistic wouldn't work for it. I'm not going to even pretend that I know the underlying reason for that, but sometimes an OLS doesn't work, and which is why. Oh, sorry. Sometimes a logistic sort of analysis doesn't work, and that's why you need to run an OLS. But generally, I'd say an OLS is better.
Okay.
But great question. Daniel, I think you had a question.
Oh, yeah, I forgot. Thank you. So I was curious about the F-stat and T-stat. I know, like, I see the T-stat are related to the specific features, but the F statistic is like as a whole, is a high number better? Is a low, like, what is, do you mind going into a little more detail with the F-stat?
Yeah, absolutely. So T-stat, as you know, it is feature specific. F-stat is model general. Both of those we'll get. So if in R squared is kind of looking at the overall kind of the degree to which the variance in your features kind of maps to the great feature, the variance of the labels, and F-stat looks at the kind of, I guess, the strength of that relationship. So if the first one is saying, are these trending in the same direction? The second one says the degree to which they trend together. And in this case, the higher the magnitude, so it's kind of, you almost need to think counterintuitive. So if a p-score, we want the lower the p-value, the better. For a T and F, the higher the value, the better. And again, there are certain critical thresholds, and those numbers are not absolute. You do have to kind of interpret that, which is why you would have to, if you would have to go and look up, and it depends on the number of features in your data. It depends on sort of a few other things, but there are critical threshold values that say when it's above a certain level, it indicates that sort of these values are closely correlated to one, such that the explanation of one very closely ties to sort of the value you see in the other. So generally speaking, the higher the value, the better.
Okay. And there's no maximum, because like you said, there's a table, so it would depend on like how large your features are and stuff. So there's not like a threshold, like the maximum F stat you'd ever see is some number.
There may be, yeah. So it's a number. It's not a probabilistic thing. So like an R-squared, the max value is going to be a 1. A p-value will
Okay.
be also a 0 to 1. So there's a max and min values to those. For a T and a F statistic, I'm not aware of a max value for that.
Okay, thanks.
Yeah. So yeah, great questions, guys.
I have a question, if you don't mind. So about those sample regression results earlier, like a couple minutes ago, you mentioned that because we notice a couple things, we can just drop certain features. Can you elaborate on that again? Like, what did you notice and which features can we drop?
Sure. So the things to look at here. So really the two things that are important. So if you look at this table, right, these things here tell you overall performance of your model on a model level. This breaks down your individual feature. So feature by feature. So, this thing gives you the coefficient associated with the feature. So again, so there was that conversation about the magnitude of the coefficient being sort of indicative of its relative importance. And then these two features here are the p-value and the t-value. And again, so the p-value says, what is the probability that the results that I'm seeing for this feature are the result of just random chaos, that there's no relationship between my label and this feature, and that these are just random chaos. And again, whatever that critical threshold value is, whatever that, I think it's called an alpha score, whatever that value is, and usually it's a 0.05, anything that's less than that, you say, okay, there's a relationship here. The chances are that it's not random chaos. The chances are that there's a real kind of correlated value there. So that would be the first thing you see there is whether or not there's a critical threshold here. And so just looking at this, if we take that 0.05 threshold, we see that our first two values are related. Everything else sort of fails that we're seeing here. So we would say, okay, I could reasonably drop all these features and I probably wouldn't lose much of any predictive accuracy of my model. And then the associated thing is the t-score. And again, that if your p thing is just telling you, is there a relationship there that is likely not chance, the t-score really gets at the magnitude of the relationship and the covariance between the things you're looking at there. And again, there are certain thresholds with it. So obviously, 118 is greater than 16, but whether or not both of those features numbers are significant, you would have to look up in the table and see what the critical threshold for that value is. But
I see, got it.
Yeah.
Thanks.
Yeah, absolutely. Okay, so I think that kind of bleeds into my next discussion, principal component analysis, or PCA. So, so I was just saying how we have all these nice things, we've done these statistics, we can drop all these features that clearly aren't doing anything, right? So let me put a bookmark in that and let me get back to why that isn't necessarily the case. But let's start talking more generally about the curse of dimensionality, which is something that we have talked about throughout the course. We have sort of hinted at, talked about in relation to overfitting and other things. Hopefully, and maybe you have some intuition for why that is. Hopefully, by the time I'm done with this section, you guys are like, yeah, man, I got it. But let's talk about sort of what happens when you add features. And by the way, this is actually a homebrewed meme, but this is true. So, generally speaking, if I'm adding relevant features to my training data, if I add features that have explanatory value, unsurprisingly, my model performance will improve. However, if I add irrelevant features, if I literally just start adding features that are, zeros and ones or just zeros, I literally just add a feature that says 0 and it's all zeros, and 1 that's all ones. Just literally adding noise. My training accuracy, and this is an important thing to note, not my testing accuracy, but my training accuracy will still improve. So I can add just complete worthless data and my model training accuracy will still improve. And so an important kind of thing to note here is that, and obviously if that's happening, what that doesn't mean that my model is improving. What that means is that I'm overfitting. And we're going to take a look in a moment at sort of a concrete example that sort of helps to do that. But it's the idea that, again, the more data you have, the more likely I'm going to lead to overfitting. let's look at a specific example I found online. Let's talk the cats and dogs. Ooh, my framing was not great. Okay, that cut off a little bit. All right, whatever. So here's kind of a great example of this. I want to build a classifier model for determining cat or dog. And currently I have a single, whatever the feature is, head size, color, nose size, whatever my feature happens to be. And I have 10 data sets. So this is a 5, whatever our sort of our unit of measure is, this is a 5 thing, and I have my 10 data points here. So if you look at the density of my data here, it's 2, right? Because essentially I have 10 samples. I have sort of a unit intervals of 5. So clearly my data is very dense. Also very clearly, there is no way in heck I'm doing any kind of linear classifier with that. So let's say I do some kind of augmentation, transformation. I add a second feature. Suddenly the area grows exponentially. Or not, sorry, the area grows, well, the area grows linearly, but the density drops exponentially. I go from an area of 5 to an area of 25. I still have my 10 things here, but my density drops from 2 to 0.4. So there's an exponential decrease in density. Then let me add a third feature. Suddenly my relative area is 125 for my little 10 samples. Now my density is 0.08 samples per interval. And here, this is kind of spread out so thinly that voila, I can get my clean hyperplane, right? That was the whole trick we did with kerneling functions and with other things where we said, you know, if I don't have a clean separation, I can sort of take it to a higher dimension and I can do that. And so the result of this being that the higher the dimensionality that you go with this, it becomes at some point, because of the sort of the exponential growth in sparseness, as you go into higher and higher dimensions, the probability that you will be able to achieve sort of a clean separation of your classes essentially goes to 1 as your dimensionality increases. The probability is essentially infinite that you will successfully do it, even though that's not actually a clean thing. And if you kind of go back to your thing here, if you sort of take it down to a lower dimensional space, you can see that the resulting classifier has just completely overfit. And it's taken all of these specific odd one out things that aren't representative of the general population, and it's sort of built a model specific for that. So the idea being that if you would have, and this is, I think, you know, we talk about like the relationship between dimensions and data and how dimensions affect it. But because you're adding a single feature has an exponential decrease in sparsity, you would have to grow your data set exponentially to offset the chance of overfitting. So hopefully that kind of puts into perspective the degree to which sort of adding that additional feature can have sort of a real cost and a real impact on the potential for overfitting. So yeah, so you know, as Daniel's indicating, what we're looking at here, right, is that there's this sweet spot. We want to find a model where we have sort of, we're capturing as much relevant data, as much relevant information as possible, but we're reducing the dimensionality such that we're essentially not playing on easy mode, where we're kind of forcing the model to determine general trends in the data and not just kind of selecting this perfect little divider. So, you know, just like with everything else, there's finding that sweet spot where I'm feeding enough relevant information to my model to be effective in classifying, but I haven't kind of fed so much information to it that I've just overfit the heck out of it. And, you know, it can kind of classify perfectly, but it won't generalize in the slightest. That's our goal. That's our hope. Let's talk about how. So firstly, so if you're thinking about that, you're saying, well, hey, you know, we already solved that. We got this little thing here. Just run a regression, find the features that aren't really doing much for us, and just cut them, and we're good to go, right? Why not just trim them? Hopefully that's what you're thinking, and You're like, okay, I can just go home. Here's potentially the problem with that. Sometimes an individual feature may not seem to have much importance. Either, maybe it is statistically significant, but the coefficient is unimportant. This is where we were getting at before with just looking at coefficient analysis, or maybe it in its own right doesn't have direct statistical relevance. But there's also the, oh, by the way, is the lawnmower in the background, is that making a lot of noise, or is that okay?
I can still hear you fine.
Okay.
Yeah, we can hear it, but it's fine.
Okay. All right, cool. So the thing is that there may be an underlying pattern to the data, an underlying sort of, sometimes you're not capturing data directly, but there's an underlying feature in your data that is relevant that you do want to capture that maybe is inferred or represented in your data. So one example of that might be, let me think about this. One example of this may be, for instance, intuitively we know that age is important to your model, right? Age may be important to predicting a person's health, a person's mortality, but you don't have age, you don't have data on that. What you do have is maybe proximate indications for that. So maybe you have data on what apps, let's say you're looking at cell phone usage data. You're able to see like what apps the person's using, how much time they're spending on their phone, things like that, right? These things maybe individually, if you ran a regression against that and mortality, you wouldn't necessarily see a clear relationship, but in concert with one another, sort of fit together, they paint a picture of age, because you can infer certain usage, certain behavioral characteristics will relate to age. There's that underlying kind of relationship there that isn't necessarily explicit in your data, but is implicit and is, by feeding in all that data collectively, there is that pattern. It's just those individual features aren't fully capturing it. That might be one example. Another example is a lot of these features may be correlated. So I saw an example of this when it comes to synthesizing image data, and certain cameras are more sensitive to, so you have your RBG kind of filters, your red, blue, green filters. And certain cameras, certain lenses will be more sensitive to certain sort of colors. And so may sort of bias the collection to one thing, but and may undersample some of the other ones, even though they're there. So keeping sort of not just dropping, for instance, green may be important because some of the red may not have been captured accurately and may have bled over into green. But so you kind of need to have all three of those there to capture the underlying pattern sometimes. So that's kind of the problem. And that's why just doing this sometimes isn't sufficient, because the data is often a lot messier and a lot more codependent and covariant than this kind of clean analysis would be. And so what we need is to think about the data in a little bit of a different way. The kind of the key insight for what we're going to do with a PCA. Okay, I'll get to that in a moment. The key way to think about this is to say, I've plugged in all of these features, and these features have created kind of a data set. And if I plot it out, right, there's this kind of mix of data here. That data has a certain shape, certain contours, certain sort of characteristics of that data. And so the question is there a way of capturing that distribution, that spread, the shape of that data in a way that's independent of those features? So I have this pattern, I have this shape of the data. And right now I've plotted it based on those features, but that shape is theoretically independent of the features. And is there a way that I can maybe capture that shape and sort of remodel that feature, so I get the characteristic shape of that data without being tied to the specific features? So that's the insight, and that's the intuition of what we're trying to do with the principal component analysis. So with the PCA, you're essentially trying to, again, model the shape of your data independent of the features that gave you that data in the first place. And so essentially what you were doing with PCA is you're taking you're deriving a set of orthogonal and independent eigenvectors that explain the maximal amount of variance in your data. So if you look here, we have, so this is kind of an example here where I have data that's plotted around these two features. And then I say, okay, well, let me reparameterize them in terms of these eigenvectors that explain the maximal amount of variance that I'm seeing. So as you can see here, the first dimension here, if I plot it along this axis instead of this axis, I can kind of explain the variance along here. Then the second dimension, I plot along here. So I'm kind of recasting that. And so then the kind of the cool thing about that is I can dramatically reduce the size of my dimensions, because by sort of capturing the highest amount of variance with each successive feature, I'm sort of capturing as much of the information, right? If you think about this as sort of conveying the underlying information or pattern in my data, by modeling it and reparameterizing it this way, I'm maximizing the amount of information I convey with each dimension. And so therefore I can kind of cut a lot of the sort of the I guess the stragglers, if you will, a lot of the sort of the low information dimensions, and feed as much relevant information in as feature condensed to space as possible. So, and again, so you can kind of see here, so this is, I think, kind of a nice way of looking at this. So this is sort of the proportion. So you can sort of plot the relative impact of each principal component sort of as part of its overall explanation of variance. So for instance, just grabbing the first principal component, this is sort of a sample model. In this case, it captures about 50% of the variance. So just having one feature explains 50% of the variance I have. If I go to two features, I'm now at, oh no, I'm sorry, that's not 50%, it's like 30%. Then this gets me up to 50%. Three features gets me to 60. Four features, roughly 70. By six features, I'm up to 80% of the explainable variance. And so if I sort of decided at that point to trim my model and say, okay, I'm only going to represent the first kind of six principal components, my resulting model will sort of capture 80% of the variance in the label that I've produced. And by the way, we can kind of see that pretty dramatically if we look at the code. So here I have also sort of dimensionality reduction. So I mentioned that, when we went hot and code, when we did things, it kind of blew up the dimensionality of our features. And so you can see here how that looks. So if we just call the shape method for it, we can see here we have 18,000 rows. We've gone up to 65 features when we went hot and code. If you remember, our original data was 1, 2, 3, 4, 5, 6, 7, 8. We had 9. So we added 56. Yeah, we added 56 features just by sort of one hot encoding our data. So that's significant. As you can imagine, that's pretty substantial amount of overfitting is probably happening. Let's see. Where's my, okay. Yeah, so you can then kind of run PCI on this. So here in this case, you kind of define a method. So you would import, in this case, it's a decomposition library from scikit-learn. You define the specific approach we're going to take, PCA. You define the number of principal components you're going to use, and you can vary that. It's just the amount of principal components you want. And then you can kind of do, again, your fit transform to your data to produce a new data set that's only 4 dimensions large. So if I output it, this is what my new data set looks like. Now I'm going to run a logistic regression on it again. And if you remember from up here, what was my accuracy I was getting beforehand? Okay, so beforehand, I was getting 98% accuracy. Now, if I run that again, I'm getting almost a 90% accuracy. And remember, I've gone from 65 dimensions to 4 dimensions, but I've captured enough of the underlying information in my data that I can still achieve a 90% accuracy with that. And probably if I tried to optimize that, there's probably a number, 8, 9, 10 or whatnot, where maybe I'm even exceeding my original performance, because at that point I'm addressing maybe some overfitting issues.
I know.
Yes.
Does this package automatically calculate like what the optimal feature number is? Like
Oh.
you don't have to manually choose like 4 features, right?
So unfortunately it doesn't, because the optimal feature amount will depend on your model. And so at least I'm not aware. So let me clarify that. I'm not aware of an approach that would allow you to kind of automatically determine the optimal amount there. There might be. So I want to say that I'm speaking from a position of relative ignorance. But the way I've run this is similar to what we did with like KNN, where I would run through different parameters, where I'd sort of do a for loop and I would say, okay, n components 2, 4, 6, 8, 10, 12, whatever, whatever my iteration is, and then run through that and then see and then plug in that data frame and look at my results.
Okay, so this is like tuning a hyperparameter.
That's exactly what it is. Yeah.
Okay.
Yeah. And you can also probably, and I'm not sure how to do this, but you can probably also output with your principal components. You can output your cumulative variance. So you can probably see, and I'd have to look up the precise method to do that, but you can probably output like certain thresholds. You could say, okay, well, what number of principal components will give me, let's say, a 95% threshold, if that's where I kind of want to try the line. You might be, I think you'll be able to do that as well, because you can plot cumulative variance. So you should be able to determine that number too.
I have another question about this.
Mhm.
So would it be worth calculating like the training accuracy as well, like both before and after doing PCA, just to make sure that the process is actually reducing your overfitting, or also to determine whether you need PCA? Because if with 65 features you're not overfitting, then I'm not sure what you're gaining.
Yeah, that's a fair point. So generally, I think the reason I'd be hesitant to say looking at your training data is because usually your testing data is what matters most. Because so let's say you're looking at your training data, and let's say your training data is looking really good. You're getting near 100%. Well, that could be a sign of overfitting, or it could be a sign that your model is performing really well. And then if your training data goes down, if your training data drops from 100% to 95%, you might say, well, maybe that's a good thing because now I'm not overfitting as much. But it could also be that the overall performance of my model is also falling. And so that's kind of where you need your testing metrics to be able to say, okay, well, is this actually, am I decreasing my overall model performance, or have I sort of reduced my overfitting in my training such that my overall performance increases? But yeah, really great question. I should also mention this before I forget. Another reason you may want to deal with PCA, do PCA, is it can be very, very useful when it comes to big data problems. So again, not something that we have explicitly dealt with when we're looking at the problem sets that we've dealt with here, but intuitively, we've talked about instances where you're dealing with thousands of discrete features and millions or even billions of rows of data. And at that point, you need to start thinking about how to sort of economize or optimize the analysis that you do. And it's precisely in that instance where PCA and dimensionality reduction in general can be so critical. Because at that point, you just simply can't, think about your poor gradient descent function and your updating functions if you're literally trying to update thousands of individual parameters to try and kind of optimize for that. So for that reason, PCA can be an immensely helpful tool for dramatically decreasing the amount of computational sort of energy required to sort of get a successful model. So that is PCA in a nutshell. And again, the code that you would need to do that is in the workbook. We just kind of walk through it very simple. And for project 3, you're asked to do that. One other thing I should mention with PCA is I talk about black boxing it before, and I talked about like that with neural nets and everything. PCA is another example of black boxing, because if you think about it, what we have explicitly done is we've removed all of these explicit features, and we've sort of reframed our data in terms of these principal components, which again is great from a dimensionality reduction standpoint. It's terrible in terms of an interpretation standpoint. Because, what does this mean in plain English? What does this first principal component mean? What does the second principal component mean? Well, I don't know. It's not translatable in terms of real world features. And so this is kind of an example where where you're effectively black boxing your data. Yes, you're improving performance. Yes, you're doing a lot of really useful things, but in terms of kind of explaining it, in terms of talking through, here are the features that are really important. Here are the features that have impacted this model. Here's, what we found was important to that. You've kind of effectively blinded yourself to that. And that's precisely why analyses like these are so helpful in conjunction with sort of a PCA. If you think about this as being just, doing what you can to really kind of turbocharge the performance of your model, you still kind of need this in case you need to sort of talk about the underlying characteristics of your data and what really is important in terms of what gets fed into your model and what doesn't. So that's kind of an important thing to note in terms of PCA and one of the effects it has. And that's why, sometimes, well, not necessarily, you wouldn't necessarily do dimensional reduction, but you would at least want to do it in concert with sort of a statistical analysis to kind of help understand feature importance and significance. So that's it. And also shout out to the Mean Girls. It's always a good day when you can throw in a Mean Girls meme, honestly. I just feel like the world has too few of those. Yeah, any questions on that before we move on to bigger and better and brighter things? All right, cool. This is the part of the class where I have lulled you all into a semi-comatose state. Excellent. Okay. Okay, yeah, sorry. There's also, I should mention, there's also an extraction augmentation component of this too. Sometimes you can use PCA when you are trying to kind of, here's kind of a fun thing here. So if you imagine this plot here as a map of Manhattan, okay? So imagine this is Manhattan Island here. Doesn't really look like it, but just imagine that it is, you have Midtown here, lower, Midtown, Uptown, Downtown, all those components here, right? And it's kind of on this angle. You have latitude, you have longitude. One thing that sometimes may be useful from a data extraction feature may be to reparameterize that data in terms of its principal components. So as we can see here, right, think about Manhattan Island because it's on a slope, it's on a slant. This long axis here can actually be sort of more useful, more sort of telling of its relative position than just looking at latitude. So sometimes you may also want to use PCA to sort of transform data along sort of kind of reframe it in terms of axes that are most important to it. And I think that the great example of that is longitude, latitude, and maps. That, again, if you reframe your data of Manhattan in terms of lengthwise and widthwise, that can actually be a lot more useful in terms of what you plug into your data. So yeah, I did want to mention that too, because that's kind of a cool trick that you can also use PCA for. Okay. It helps when I actually read the slides that I write, doesn't it? Yeah. Okay. So, okay, I did want to mention this. I sampled, so let me actually frame this as a question. I kind of sampled the people who showed up to office hours in terms of like how they felt about ensemble methods, because I know professors spent a good deal of time on that in lecture. And the general consensus was we kind of had covered that. So I didn't prepare specific stuff for that. Sorry, I bit off a lot of food just now. But I did want to mention that in the labs, that sort of supplemental labs that we provide, there's a week 6 lab. So Orpaz posted, I forget which week, it's up on CCLE, but he kind of threw all of them together. But I believe it's under the week 6 one. There's this notebook called DTRF, which is Decision Tree Random Forest, that does a really, really great job kind of walking through decision trees, talks a bit about entropy and uncertainty, talks about kind of determining both the sort of the overall entropy of the model, talks about gain functions for that. I'm going to mention that because for the homework, that's kind of important to know this. So this is like a really nice walkthrough of it. Then it walks through some coding thing for decision trees. It walks through bagging steps. It talks about the difference between bagging and a random forest, talks about implementing a random forest, talks about sort of using an out of bounds error to calculate that, talks about boosting as well. So all of this code is there. It's there for you to use for both the homework and the project. So that's sitting there on CCLE. And if you have not accessed it, which I have a kind of suspicion maybe you haven't, just know that it's there. But if you do, and I want to just mention, if you guys do want to talk about sort of ensemble methods and entropy-based approaches to classification, we can totally kind of segment out some time, maybe next week or the week after, to talk about that. So I guess just, are you guys good with that and the code we're giving you, or do you actually want to spend some time talking about that? Okay, I think people are feeling good about it. Okay, cool. Then I'm feeling good that I kind of made this into it. But do go use that code. It's there. It's a resource for you. You know, just be aware that that's there, and that'll help you for both the homework and the project. So last kind of official thing. So I have 2 more things that we can cover. The first is starting neural nets, which Professor didn't cover that on Thursday, did he? I wasn't able to attend that lecture, so I don't know what he covered Thursday actually. What did he cover Thursday? No, he did not. Okay. Okay, cool. All right. So obviously we're going to that's sort of like the last big topic we're going to cover in course. I think it'll be neural nets, and then it'll be unsupervised learning approaches, clustering approaches to learning. I think those are kind of the 2 kind of big technical things we're going to be covering. So I figured we could kind of talk a little bit about that and just kind of introduce that. And then I have, if we want to talk about this, we can kind of backtrack a little bit and talk a little bit more about probabilistic learning methods. So specifically about naive Bayes. And we covered that in lecture a few weeks ago. That was in project 2. And the reason it might come up again is it's one of the few models that we could actually realistically ask you to solve by hand on an exam. So it might be worth going through an example of that. I don't know if we want to cover that this week or not, but I have some slides on that. So that's where I'm at. What do you guys think? You want to cover that? Yay, nay?
Yeah, please.
Any vocal no's in the audience?
Can you cover how it's different from our other classifiers? Like what a probabilistic learning is versus others?
Absolutely. So actually, let me ask you guys this. Do you want to do neural nets perceptrons first? Do you want to do naive Bayes first? Either or, neither nor?
I think as long as we hit naive Bayes before the exam, that's cool. Because I mean, we already know how to use it, but the neural nets was probably more applicable sooner, if that makes sense.
Okay. So let me knock this out first. How does that sound? If you guys want to do, I'm taking you guys want to cover both today.
If you have time to do them both, yeah.
I got time. We got time. All right, let's do them. Okay, so kind of interesting thing about naive Bayes is naive Bayes is conceptually, so it's a form of probabilistic learning. And so let's, I guess, talk a little bit about that. It's kind of interesting taking a step back if you think about the different approaches we've taken to classification in this course, because you would think on a superficial level, right, to classify data is sort of, it's all one and the same, but we take these really, really interesting approaches to it. And sort of one, I guess, framework for it is thinking about your data in a sort of in a geographic, in a geometric space, right? And thinking and using its sort of its physical distance, its physical proximity, and sort of relative relationships, use that physicality to classify it. So examples of that are KNN. Obviously, we literally look at nearest neighbors, and then something like an SVM, where you literally draw that hyperplane separation between your data in that kind of multi-dimensional space. So there's that one approach of looking at it as physical entity in n-dimensional space, and then classifying based on that relative space. Another way of thinking about this is probabilistically, of saying, well, let's think about sort of the probabilities associated with certain sort of, I guess, kind of feature types, certain values associated with features, and then let's kind of assign probabilistic chances of a classification and use that to sort of make a decision. And so for that, obviously, we used something like logistic classifiers, and then also naive Bayes as an example of leveraging probabilistic approaches. The other, I guess, kind of big approach that we've sort of studied so far has been using information theory, using entropy, using ideas around kind of entropy and loss to sort of split your data and do it in a way that sort of most cleanly helps you segment your data. And so, both decision trees and random forests and whatnot, thinking about it in terms of that and framing your kind of approach that way. So it's kind of cool to think about like all the different ways we can think about splitting your data and looking at your data in different ways. So, I mentioned naive Bayes in the context of a probabilistic approach. The other thing that's kind of interesting about naive Bayes, I think uniquely, and almost segments it with a KNN, is that there's no implicit learning to a naive Bayes. Unlike a logistic regression where you learn, right, you learn that decision boundary, you learn that quadratic formula for that odds ratio, or an SVM where you learn that the quadratic form for your linear divider. For a naive Bayes, there's no implicit learning step. The data itself is the model, much like a KNN. And by the way, I'll mention this kind of as an interesting aside. I took a grad level database and knowledge base course at UCLA. And for our final project, one of the things that we did was implement both a KNN and a Bayesian classifier in SQL. And because both of these models, you're literally just doing basic arithmetic. You're not, there's no active learning about it. You can implement those basic functions in SQL. So I guess that's kind of a cool aside with that. But that's sort of another thing to note about naive Bayes is the data itself is the model. There's no learning step associated with it. You just take the data as a given, you use it to calculate the probabilities, and you output a probability based on that. So in that context, I think we've all seen Bayes' formula to death. Probability of A given B is equal to probability of B given A times probability of A all over probability of B. In this case, A is our classification. So if you're thinking about this as a binary classifier, it's the probability of either a 0 or a 1. It's probability that the class is a 0, the probability of the class is a 1, and B is our particular set of values in our data frame. So given this particular sort of set of values for x1, x2, x3, x4, x5, what is the conditional probability of 0 given these features? What is the conditional thing of 1 given these features? And then of course, it's sort of the overall probability of that label times the conditional probability of those features given that label. do I talk about this? Sorry, let me see where I talk about it. Okay, no. Some other things to kind of note about this. Part of the naive aspect of naive Bayes is we don't sort of learn I mentioned we don't learn anything about our data, and we make some simplifying assumptions for our model. The first is we treat all of our features as independent. So, and as a result, the conditional probability for the total sort of set of features. So if B is our total, x1, x2, x3, x4, x5, we treat that. So when you have the joint probability of statistically independent features is just the product of their individual probabilities. So you would just multiply the probability of x1 given A, x2 given A, x3 given A, x4 given A, x5 given A. You just multiply them together and then you get that joint probability. And that's your conditional probability. So that's the first simplifying assumption we make. The second simplifying assumption we make is we can drop the denominator. Because what we're going to do for our naive Bayes is we're going to make two calculations. We're going to calculate the probability of 0 given my features and the probability of 1 given my features. And so the probability of those features occurring, that denominator is going to be the same. The only thing that matters is my numerator. So for the sake of the calculation, I just drop that thing and I just calculate this thing here, the numerator. And that's what you kind of see here. So if I'm trying to predict the probability of a given class, of a class given these particular x1 to xn features, I'm essentially that's equal to the probability of those particular set of features given that class times the probability of that class. And I do that calculation for both classes, so class of 1 and class of 0. So,
sorry, do you mind re-explaining that? I was taking notes on something you said prior, explaining why we can drop the denominator.
Sure, because in this case, we're doing a comparative assessment. We're essentially going to be calculating this twice. We're going to be calculating the probability of 0 given B and the probability of 1 given B. And we're going to look at whatever one, essentially the way a naive Bayes works is it just says, okay, whatever probability is higher is the one we take. And given that these two denominators are the same, right, the probability of B doesn't change between those two calculations. The only thing that changes is these two. So really all we care is the relative value of those numerators, whichever one is higher is the one that we take.
Okay, thanks. That makes sense.
Yeah. So for that reason, we can just simplify and drop the denominator and just take that numerator. So this seems, I guess, theoretical, but we'll work through an example and you'll see it's actually conceptually very easy. So, and to get there, we're going golfing. So let us imagine that we have a data set and we have a data set that has a total of 14 values. You're only seeing a subset of that. And we're trying to predict whether or not you are going to play golf. And it's a binary classifier. So it's either a yes or a no, a 0 or 1. And we're given these 4 features, 4 categorical features. Outlook, where we have things like rainy, overcast, sunny, temperature, hot, mild, cool, humidity, high, normal, I guess probably a low. And then windy, it looks like it's a binary true or false. So we have these 4 features here. And then we want to predict if I'm given a particular set of features, in this case, so outlook will be sunny, temperature will be hot, humidity will be normal, and windy will be false. I want to predict whether or not it'll be play golf. So if you think about how our model is set up here, I'm going to calculate the probability of play golf given sunny, hot, normal, false, and that's equal to that. And I'm going to predict the probability of don't play golf given, again, that sunny, hot, normal, false. So that's my challenge here. And the way to kind of just eyeball this is to say, okay, well, so you can create sort of a series of tables here that sort of lay out the probability in terms of each feature. So I have a total of 14 samples, 9 yes, 5 no. So that already, by the way, gives me a little bit of a probability of yes and a probability of no, right? The overall probability of yes is going to be a 9 over 14. My overall probability of a no is going to be 5 over 14. And I can begin to look at my conditional probabilities of, because remember, what we're solving for here, so we need to kind of solve for these individual pieces. So I already know what my P of A's are. It's 9/14 and it's 5/14. So for this, I need to look at for my total number of either play golf or not play golf, what's the ratio that falls under those particular variables. So in this case, sunny. So if the total number of times I play golf is 9 and 2 out of those times was sunny, the conditional probability of sunny given that I played golf is 2/9. And concurrently, the conditional probability that I didn't play golf is 3 because there are 3 times when I didn't play golf. So 3/5. So that's kind of how you read that. So these are here. So if you're looking here, these are my 4 features. This is my total play or not play. For each of these, I'm getting the conditional probability. I'm getting my probability of B given A. So in this case, for humidity, in this case, out of the 9 times total, 3 of the times I played when it was high. So that's 3/9. And then 4 out of the 5 times when it was high, I didn't play. So that's how I get my individual probability. That's how I get my individual conditional probabilities. So now I see how I have my P of A. Now I see how I have my P of B given A. So now I can just plug them in to get this. And so if you remember, I said all we have to do is multiply because we're treating these as statistically independent. So all I have to do is multiply all of these together, and then I'll get my term here. And that's exactly what I'm doing. So first I'm going to calculate the probability of yes given today. And remember, today here is sunny, hot, normal, false. So sunny given yes is going to be probability of hot given yes. So that's this. Normal given yes. Wind is false given yes. And sunny given yes. And then times probability of yes, P of A. And just plug in those numbers. So in this case, sunny given yes is 2/9. What's next? Hot given yes is also 2/9. Humidity given, normal given yes is 6/9. False given yes is also 6/9. And then my total probability of yes is 9/14. So I get that number. I plug in the same set of variables for no this time. Oh, why did that turn out all nice and formatted? No, it didn't. I don't know, but okay, interesting. And I get that number. And so I can theoretically stop there because as I have already, I can see that the probability of a yes is much higher relative magnitude to the probability of no. But if I want to, I can normalize it too, which is just divide the probability by my cumulative thing, multiply by 100, I get a nice little percentage here. And this got cut off a little bit, but essentially it's here. Let me just size this. Okay, there we go. Now we can actually see what we were saying. And so that equals 67 and 33% respectively. So obviously I am twice as likely to go golfing given these conditions as I am not to. So if I was to classify it, I would choose yes. So yeah, easy, breezy, beautiful. Any questions on that?
Or girl. I guess I have a question. What if what if your data set has a lot of features that are highly dependent, and then is this model just going to be completely wrong then, or stands to be because of the simplifying assumptions it makes?
Yeah, so great question. So naive Bayes kind of similar. I would use sort of a similar if you have like a what's it called, a sort of a warning. If I were to write a warning label for naive Bayes, that would clearly be one of the things you would say. Here, just like with a KNN, we are making very specific, very simplifying assumptions about a naive Bayes. And one of the kind of surprising things given these simplifications is how relatively good a naive Bayes performs, all things considered. Like, I don't know if you saw that in like project 2, but maybe your performance took a little bit of a dip, but like it worked surprisingly well. Generally speaking, you would not, naive Bayes is not usually your end model. You don't kind of end up with a naive Bayes. A naive Bayes is usually just like a KNN. It's a good starting model. It gives you some indication of overall performance, overall trends, but for the reasons you talked, for the reason you mentioned and more, it's usually not where you want to end up. I mean, sometimes the model is sufficient. You're like, hey, this works. It's good enough, but there's no question that you can do a lot better. And so usually it's not where you're going to end up when you do your analysis for precisely that reason. So yeah, great question. All right. What else is going on?
So is this the type of by hand calculation that we might be expected to do on the exam?
I think, yeah. So when we'll talk about this more next week, particularly when I have a little bit more guidance from Majid about precisely what's going to be in scope, but at least in the past, there's because this is an exam that's written by hand, we generally don't want for calculators. There's really only a small number of problems you can reasonably do by hand, and this is one of them. I mean, you can very easily see us giving you sort of like a small probabilistic table like this and say like, hey, figure out which one is the higher probability. And, probably would be a simpler model than this, maybe like a 2-feature model. And then just say, use naive Bayes to calculate it to assign a class or something. But yeah, this would be the kind of thing we would ask you to do. Based on our conversation, I think like KNN is another one that we could reasonably ask you to do, to say like, here are these points, classify them based on where this data is arrayed. I think that's something we could reasonably ask. Trying to think what else. If clustering is included on the exam, which I don't know that it will be, like something like a k-means is something also that you could probably solve by hand, but that's about it in terms of the models that you could like solve for. Oh, and a perceptron / a neural net. We could give you values and have you plug them into a model and get a thing. We actually ask you to do that in homework 3. Related to that, there are certain models that we can ask you to update to go through the learning step. Perceptron is one of those. Neural net theoretically is another one. I'm trying to think offhand what else we might ask you, but yeah, it would be something like that potentially. So that is neural net. That is naive Bayes in a nutshell. Oh yeah.
Rohit gave a really good question in the chat.
Oh.
Would running PCA before, or I guess you can just read it.
Yeah. Okay. Oh, interesting. Yeah. So Rohit, actually, really great question. Yes. So by definition, PCA removes sort of statistical codependence. So yes, you would be looking at statistically independent things if you plug it in there. So yeah. So Rohit, you would be right in saying that would be that would address that particular issue. It doesn't deal with all of them. So like, we assume a certain distribution to the data. We assume, we don't assume a class imbalance. That's kind of another important thing. We assume that those classes are representative of the real world. That may or may not be the case. We obviously aren't necessarily biasing one error type over the other when we do something like that. So there's still drop-downs to using a naive Bayes, but yeah, you were right to say if we did something like a PCA, that would, by definition, address statistical sort of collinearity and codependence. Yeah, thank you for flagging that, guys. All right, you wanna talk perceptrons, or do we just want to break and talk? We can push that to next week. Your call.
I'm good with covering neural nets and perceptrons.
Okay.
Yeah, sorry, I want to do the material also.
All right, you're making me earn my keep this week. So we will just cover perceptron today. There's enough just to go over with that. And specific to the exam, I think the perceptron is kind of the key thing. Perceptron, it is not a type of transformer, but it certainly sounds like that. So Probably almost all of you guys have encountered neural nets at some point. You have some basic idea, high school biology or whatnot, of sort of the idea of a neuron in general, right? So we have, if you think about it from a biological perspective, we have these dendrites that are at the kind of the tail end of the neuron. They receive a variety of input signals that potentially activate them. There is a sort of a cascading threshold, and then when it sort of crosses it, right? It's a very kind of discrete boundary, which from a classification perspective, I think, oh, that's nice. When it crosses that sort of threshold, it's either 0 or none, and then it fires. And you can, so that's obviously from a biological perspective. We can, so there's a little bit of a background on this. So this was the whole idea of a neuron, of a single, so this is kind of, I guess, the important thing, of a single neuron learning model dates back to the 1940s. And in the 1950s, they kind of formalized it. And one of the interesting things that is kind of important for this is he was able to prove sort of the perceptron convergence theorem that said that if there was a way of cleanly dividing the data using a basic learning rule, which we'll get into momentarily, it was guaranteed to find it. So you would, if you allowed it to run long enough, if there was sort of a set of weights that would sort of allow for a clean separation, it would converge on it. And as you'll see, it's kind of, it's not intuitive that would be the case, because the learning rule is actually really, really simple and really intuitive. But so again, if you know anything about like the history of AI and that, and you sort of I guess the ice age of AI and machine learning that happened kind of in the 70s and even in the 80s, when we sort of hit a wall in terms of what we could classify with our basic learning models. And it wasn't until we sort of took that neuron idea and sort of created these neural nets, where it is literally a network of neurons, of individual perceptrons, that we could overcome some of the intrinsic limitations and classify data that didn't kind of allow for that very clean sort of separation. So let's kind of, again, think back to this, where we have multiple sets of inputs. We have kind of a decision function. We have an output here. And that's fundamentally what we're looking at here with our perceptron model. We have, generally speaking, a series of inputs. And these are our feature sets usually. So this is, x1 through xn. So that's all of our features in our dimensional thing. We have an associated weight with it. And the weights are just like with the other models. When we talk about a learning step, what we are learning is the weights associated with it. So the weight that we assign to feature 1, feature 2, feature 3, all the way to feature n. We learn the weights to that. The other thing that is often the case is we have our y-intercept. We have our sort of our constant. We also call it our bias term. And so the way this is formalized is you just input a constant, in this case a 1, and then there's that weight associated with it. And then the way the neuron works is it just sort of takes that weighted sum. So you multiply your input value by the associated weight, you sum that term up, you get a weighted sum, and based on what that sum is, there is a nonlinear step function that outputs a certain value. And it could be something like a sigmoid activation, which is 0, 0, 1. It could be a -1 or a 1. You could do something like a ReLU, which is a 0 or a positive value. But there are sort of different nonlinear step functions that you can choose for your activation function. And that's kind of an important, when we talk about parameter tuning, one of the important things that you can decide for your neural net is what that step function is. But this, in essence, is what your one neuron neural net looks like. And this is essentially what a perceptron is. And so just kind of formalizing it, in this case, this step function here is if my weighted sum is greater than 0, I output a 1, otherwise I output a 0. So that would be the implicit, that would be the classifier step for this in this case. Any question in terms of how this is kind of, I guess, framed, how this model is constructed?
I haven't taken machine learning, so excuse this if this is elementary, but the constant here you just assigned as 1, and that's why it's like left out of the equation below. Would it be like, is that normally represented as like lambda, or is that like?
So you would see that, so that's represented here as the B. That's also known as your bias term.
Oh, okay, so that is the B term. Okay.
Yeah,
all right.
so that's the B term, that's the bias term. So that's the idea that that's a constant that isn't input as part of the model, but I should also know it is something that you would learn. So this is something that you would update. Part of what you learn is you learn your bias term as well. That's kind of an important thing to know. When you're doing your updating, you update the individual weights, but you also update the bias. And that's why I think it's kind of useful to think about it in this thing, to think about the bias term as explicitly being a W0 term. Because part of what you learn to optimize the perceptron is you learn the bias that you bring to the model as well.
Okay, thanks. Appreciate it.
Yeah, absolutely. But again, very sort of basic quadratic term. Each of your features has an associated coefficient. You're going to do sort of a weighted sum of that coefficient, weighted sum of that quadratic thing with the weights are your coefficients. That will output a value, and then you have sort of an output of that. And for a perceptron, it's a classification. So again, if it's greater than 0, you output a 1. If it's less than 0, output a 0, because it's a binary classifier. If you're in a neural net, you have multiple potential outputs. It could be a 1, it could be a 0, you could do -1, 1, again, positive integer value. And there are multiple kind of output functions that you can do in a neural net. But that's sort of your basic setup for a perceptron.
Quick question also, is the bias just automatically, does that start at 1 for everything, and then as it goes through it updates from there?
You can set your bias term. Your bias term, I think, can be set arbitrarily. And I think part of the whole convergence theorem thing is that it should correct no matter what you set it to initially.
Okay, cool. Thank you.
Yeah, absolutely. So how do we learn? How do we sort of get so if this is our weights, how do we get our delta in our weight? It follows a very sort of standard formula for that, where C is your learning rate. So you predefine that. So it could be 1, 2, whatever your learning rate is. That's predefined for you. T is your actual label, and Z is your predicted label. So remember, so the whole idea of the learning rate of this is I would take my existing function here, wherever my existing set of weights were, I would plug in those X values, I would get an output, I would use that to generate a prediction. And then I would see the degree to which the prediction was right or wrong. And so that's, oh, hang on, sorry. So that's my actual versus my predicted. And then the idea is this updates if you get it right, then this term here is 0 because this is equal to this. Then this is 0. So then there's no updating my weight. It's only if I get it wrong that I then update the weight. And the kind of, I guess, the elegant thing about this is this relative positioning is important because so this is my actual, my y actual, and this is my y predicted. Think about sort of what it would mean to get an error in either way. So if my y actual, let's start with a false negative, where my y actual is 1 and my predicted is a 0. Then this resulting term here is going to be a 1, which means that my resulting sort of update function will be positive. So I'm going to, because it says right here, I should have, in this case, this summed up to be less than 0. So I output a 0, but I should have output a 1, which means my weights were too low. I need to raise my weights. So if I predict a 0 and it should have been a 1, then my weights are too low. And this is going to be a positive delta in my weights. Conversely, if I predict a 1 and it's a 0, a false positive, then this term becomes negative because this is a 0, this is a 1. this is negative, my overall delta is going to be then negative. So this is kind of a nice, elegant way of like controlling the direction in which I adjust my weights. The final element of here, which is also really, really important, is I also multiply by the value of X, because it's not enough to sort of shift the direction of my weight. I need to shift it by the scale of the input. So, and remember, we talk about like how scale is important, and perceptrons, precisely because I multiply by the magnitude of my inputs, I shift the weights accordingly. I'm not like, so if I'm getting inputs in the hundreds or thousands, I need my weights to adjust accordingly. So that's why you sort of multiply by the magnitude of it. So it's just this really, really simple, really, really elegant sort of updating law for this. And the way it works, again, really, really simple. You would oftentimes be given a sort of an initial starting set of conditions. You'd be given an initial set of weights, an initial set of X values and associated labels. For each one, you sort of plug it in, you generate the value, and you then compare if you got it right or wrong. Based on that, you then update using that rule. You then plug in the next row. Based on that, you update. You plug in the next row. Based on that, you update, you update, you update, you update, you update. And so the whole idea is you continue training either until you get it completely right, in which case, you have converged on the solution, or generally speaking, there would be a timeout. Then you'd run it for a certain number of epochs. And if you fail to improve beyond a certain point, you just take whatever one has given you the best performance. And again, this kind of interesting thing that says, like, if there is a clear sort of separation, if there's a set of weights that will sort of cleanly divide your data set into two, this sort of very nice, simple thing is guaranteed to find it. So mathematically, they're able to show that, that it will solve it in finite time if a solution exists. So yeah, so I think the only thing I'll say about that, like, is that is something that I know I think that was an exam question last quarter, but like literally you could very easily be given a sort of a set of initial weights and bias terms. You might be given like 2 or 3 rows of data, and you might say, okay, plug this in and then update your weights accordingly. Go through, essentially run through an epoch and just update the weights if needed. So that is perceptrons in a nutshell.
Can you repeat that last part again?
Yeah, about like what you'd be asked on the exam.
Yeah.
Yeah, sure. So it would be the idea, like you might be given sort of a set of like initial weights. You might say, okay, your initial bias term is 1, W1 is 2, W2 is also 2, W3 is 1, let's say. And then we'll give you maybe like 2 or 3 rows of data of X1 equals this, X2 equals this, X3 equals that, and then the actual label. And we might say, like, run through an epoch of this and update your model based on the performance. So in that case, you would plug in your first row based on those weights. You generate a prediction, and then based on that prediction, you would use this formula to update your weights. And then you'd run through, and then you'd insert the next row. And based on the performance of the model, you may or may not update based on this function. And so on and so on. You'd go through the entire epoch like that. That was a question that was asked last quarter.
Cool, thank you.
Yeah, absolutely.
I have sort of a question that I'm just not 100% sure about, but whenever you change the weights, like you get an incorrect prediction, do you restart the epoch? Because it sounds like it would just matter what order you tried the rows in, right?
Yeah, it's a great question. So the way this works is that you don't restart the epoch, you continue to run through the entire thing. And then when you reach the end, you would then restart it. And the idea is essentially you would kind of keep doing that and keep updating until you would have ideally a turn where you would run through an entire epoch without updating, or you time out because there isn't a convergence.
Got it. So do you randomize the order each time you go through the epoch, or do you always go through it in the same order?
My understanding is you go through it systematically. I'm not sure if it would ultimately affect your ability to converge if you randomized it or not. I'm not sure. It might, but theoretically, I don't think it would matter because perceptron convergence theorem, again, they show that like if there was a solution, it would converge. And theoretically, if you can sort of prove that automatically, it wouldn't matter what order your data was in. So theoretically, it wouldn't matter if you shuffled it or not. But I don't want to say for sure that because the way I learned it was you just kind of just iterated through it.
Okay, that makes sense. Thanks.
Yeah. And so, yeah, and so Mark, there's a request in the chat to do an example of this. So we will definitely, so I'll wait to get confirmation from Majid that this is the type of question he would ask on the exam. I assume it is, again, just based on previous quarters, but assuming he'd be like, yeah, that would be something we would ask, then I will totally do an example of it. Yes. But if he says like, no, I'm not interested in asking that, then you know, I won't waste your time on it. But
if he says no, and I mean, I don't know, maybe I can ask you during office hours, but I still wouldn't mind seeing this kind of like walked through just so I have a better intuition.
Mhm.
So if there's time for it, I might either next office hours or next class if you have time, it'd be appreciated.
yeah, absolutely. Absolutely. All right, guys. So that's all I had on the formal agenda. Any project 3 related questions or homework 3 related questions? Or I guess I don't have much by way of exam, but if you have any questions there too, yeah. Yeah, so I think Majid did say he was going to release a practice exam. Yeah, so there is only right now, yeah, so right now we only released, I think, dataset stroke because we haven't gotten the Kaggle contest working yet. That's a whole other issue. But if we get the Kaggle contest working, we'll release the evaluation one too. Yeah, good question.
For the imbalanced data, is it okay if we do undersampling to like artificially create the 4:1 ratio?
Yeah, great question. So we will leave it up to you to how you want to handle the undersampling. So you could totally do undersampling. You could also do something like bootstrapping as well. There isn't a wrong or right answer to that.
Awesome, thank you.
Yeah, absolutely. Or the Jupyter Notebook. Yeah, so Axel in the chat. Yeah, you are free to format the Jupyter Notebook however to your heart's desire. Not a bad idea though to explicitly label each kind of section that you're doing just to make it easier for the grader to be like, oh, okay, you did part 1, you did part 2, you did part 3. But yeah, there's no kind of official format for that. Recommendation is it just yeah. So Dean, also great question about imputation. Yes, it's completely up to you. I think again, we want to in your write-up, we would like to hear kind of some reasoning for why you chose to do what you did. You know, not just for imputation, but also like what was your strategy generally for data? What features did you decide to include? What features did you decide to exclude? Why did you make that decision? And then, you know, what strategy did you choose to use for imputation? And there isn't a right or wrong answer. We just kind of want to see you go through the thought process of you know, why you did what you did. Cool.
Will the numberings for the report be updated? Because I noticed that in the requirements, it went up to like, I think 9 and 10, but we didn't have like 9 and 10 for the coding requirements. So I think that like the numbers were a little bit off.
Oh, then yeah, we'll make sure that rubric is updated. Yes.
Cool, cool.
Or at least in the grading it will be. I don't know if we'll release a new PDF, but yeah. Yeah, you will not lose points for a hypothetical missing 9 and 10.
So like if we just have something written out in a different section, like if I I mean, I don't know what these numbers correspond to, but like if I wrote something in results that was supposed to be in methodology or vice versa, is that fine?
Yeah, that's fine.
Okay.
And again, it would be up to you if you want to explicitly label or call out each thing. I think it's always useful for a grader because remember the grader is dealing with like 160 of you guys having to read through your reports. So if you hide a section in the middle of a long paragraph on page 3, the grader isn't necessarily going to see that in the 30 or so seconds that they'll be flipping through your report. So it's not a bad idea to try and be explicit about it.
Gotcha. Thank you.
Sure. Okay. So there's a question about like when you would use label encoding and when hot encoding. Sure. So label encoding. So I should just note label encoding is usually you can use it for kind of converting a categorical feature into numeric. All it does is it assigns numbers at random to all of your distinct values. You can do that. You can also do there's an easy pandas expression as type that allows you to kind of take a column and say, change that column to as type, and then you could do like integer, and that'll transfer that as well. The downside about label encoding is that there's no ordinality to it. It'll assign values at random, and I think it just does it by when it encounters a unique value. So the first unique value it encounters will assign 1, the second will assign 2, but there's no inherent ordinality to it. So if you do want an ordinal encoding, then you actually need to do a mapping function where you would say, okay, for this row, if this value, then assign this integer value. If this value, then this integer value. So you would need to do that explicitly. But okay, and then there's the question about crossing two variables, so feature crosses. So there's, I guess, a few ways of potentially crossing features in terms of, it depends on what you're trying to do with them. So you could do a feature cross as a one-hot encoding exercise where you essentially take each permutation. So if you're looking at 2 features, and you can take each permutation of a feature and you make it sort of a discrete feature. So an example of this would be, what's an easy example of this? Left, right, up, down. We have a left, right, and we have an up and down thing. And so my permute side, I'd have a up left, up right, down left, down right. So I would take each permutation, I'd essentially one-hot encode them, and then sort of learn a model where I assigned a coefficient to each possible permutation. That would be one example of doing a feature cross. If you were looking for kind of a more discrete, a more continuous approach, so there was the notion that you may want to multiply or do something, if you're looking for like associated ratios or some other kind of multiplicative or proportional or representative kind of relationship between them, you might just multiply them together. But yeah, I mean, there's, I guess feature cross is a catch-all term for the idea that you sort of assess the relationship between 2 features. And depending on how you want to frame that would depend on how you actually represent that in your data.
Would it make sense, like if you had 2 binary variables, so yes, no, and yes, no, if you added them together to get like a feature that would be no for both, like 0, 1, and 2 as the result, and like it would be kind of an ordinal hierarchy where 0 is you don't have either, 1 is you have one of them, and 2 is you have both of them?
Yeah, I think that might make sense if it made sense for that particular data. Yeah, you might want to do that. Yes.
Okay,
Yeah.
cool.
If it was sort of like an inclusive and or where it was like you said a 0, a 1, or a 2, where the 1 was equivalent across them, then yeah, I think you could do that, absolutely.
Okay, cool. Because I was thinking about doing it something like that for like medical conditions where if you want to see like if they've had in general sense like 2 different conditions as opposed to 1, like what the effect would be.
Yeah, you can totally do that. Absolutely.
Cool. Thank you.
Yeah, because there's a good example of precisely where you would want sort of that ordinal hierarchy. Okay, any other questions? All right, I'm gonna stop the recording.